Anybody here? It is very bad, right? It is very bad. That basically means that a high percentage of the nodes in the network get a throughput of almost zero. So this is very bad. Why do they get that bad performance? Because the computational cost of these digital signatures, the homomorphic digital signature, is very, very high. This is one example of a scheme. Actually, we evaluated many of them. So it's not a problem with that particular scheme. It's just a technique, is just the limitation that cryptography brings to such systems. And we have many schemes that we looked at. There is one scheme that does much better than others. It's called HOMO-MAC. It's actually not a digital signature, but a MAC. And it's the one with the black here. So you can see that it's in a class by itself because it's really kind of in the half. So it's doing much better than all these guys over here. What it's not seen here in this particular graph is that with HOMO-MAC, it limits the performance. It relates to how many attackers you can tolerate. So unlike a digital signature where you generated the signature and for most of them it doesn't matter how many attackers you have, in this particular case it does matter. But I don't want to get into more details. It does does better than the others. So what we wanted to do, we wanted to see, is there a way we can move that bar? We want what ideally you want for a system. If you ask anybody that uses any type of system, they don't want to feel the security, the cost of security, and particularly when there is no attacker in the system. So what we're trying to see is, can we have some type of solution where the performance of the system is very close to the unsecure system when there are no attackers, and maybe we pay some penalty when there are attackers, but not to the level that the system becomes unusable. So we say, okay, if we cannot use crypto because crypto has this problem, is there any other way we can do? So one thing that we can do, and that's what we came up with the idea. Well, first, if we don't want to use crypto and we want to use what is very cheap, is there these checksums that involve just linear transformations. So those are basically multiplications as opposed of exponentiations, which all these homomorphic schemes require. We say, okay, we're going to do something like that. So we're going to create we're going to have the source creating a checksum that is disseminated periodically. We're going to have also the timestamp when it was created. We know that this checksum is sent authenticated, so nobody can then inject it. And we can use that to check if a packet is coded correctly or not. But there are two caveats here. First of all, this is not a hash. So because it's not a cryptographic hash, it is not pre-image resistance or collision resistance. I don't know how many of them. Actually, there are some people here that do crypto, so you should know what pre-image resistance is and collision resistance is, right? So it doesn't have those properties. So then the whole trick is, okay, where do you get your security? What prevents an attacker from forging packets? So the whole trick in our entire scheme, it's actually in the way the check is enforced. When I'm going to check, so what the nodes are going to do are going to check packets against these checksums that are received periodically from the source. The whole trick is these checksums have to be created by the source at a time that is after the packet was received by the nodes. Okay? And I will explain why that is the key. So let's look at a very simple example. So I have the source, I have an attacker, I have time, and I have the correct node. Because this is not a cryptographic hash, that means that when the attacker node A sees the checksum CS1, because this is not a cryptographic hash, he can actually generate a packet P that will match the checksum. No? If this would have been cryptographic, that would not have been possible. But in this case, it's possible. So then attacker A thinks he's smart. He's going to set this packet P to B with the goal to pass the verification scheme. And the whole trick is that this packet P that was received by the correct node B will never be verified against the checksum CS1. It's going to be verified against another checksum that was created at a time that has to be bigger or later after the packet P was received by B. So in this case, it has to be bigger than T3. So CS1 will never be considered as a point for verification. So if you really want to see what is really the key to make this work, is this particular slide. Now, to actually have this working in a system, we'll see that we have to get into more details, but that's really the main idea. So in other words, again, the fact that the fact that the attacker has can see these checksums in the clear doesn't reveal any information. What is important is that an attacker cannot inject checksums, and that's why those checksums have to be authenticated and they carry timestamps. So attacker cannot inject, cannot modify them. So let's look a little bit at the details. I'm going to show you two systems. First, I'm going to explain the main idea with a system that is called DART, and then I'm going to show you how you can improve over that to optimize the system even more. So we can express, I'm not going to get into all the details, but actually you can express mathematically what that checksum generation and verification means. This checksum, it's random, so the source will do this periodically. Now, there are some elements that we can use in our design to control the size of the checksum. We don't want the checksums to be very large. We want the checksum to be very small because that's overhead. There are some advantages of our scheme. For example, there are no false positives, right? So and also that the verification, again, because the checksum it's a linear combination of the packets that were sent. The verification is really a multiplication, a matrix multiplication. So it's actually very fast to verify something like that. We can also do what all the systems actually do when they propose verification for packets. And I bypassed this first because I wanted first to give you the idea. But the reality is that systems, including our solution, you never verify one single packet. You actually verify a batch. Why? Because that, again, gives you better performance. So as the other schemes, we can also do batch verification. And in case we can say that they're all valid. If they're not that valid, we can figure out which packet was the one that was polluted. Again, very fast, so that's not an issue. Now, in terms of how would you take this and integrate it, if you remember the first slide that I showed, not the first, but maybe 4 or 5, when I was showing you how intra-flow network coding system work, the changes that will happen now is that when packets are received, coded packets, they cannot be forwarded immediately. So if you look at node D, he's going to have 2 queues now. Packets that are verified, packets that are not verified. So the ones he can verify a packet only when he received checksums that have timestamps after the times when those packets were received. Then he can put them in the verified. If there are enough of them, he can code. He can send them later to the receiver. When the receiver has enough of them, can decode. Okay. Now, with this scheme, we can actually analyze, we can tell exactly what is going to be the computation overhead, the communication overhead. We can control how big the communication overhead is, and I have here some examples. What will be, there are certain parameters that control the layout of the network coding in terms of how big the coefficients are going to be, in what group are you going to do these operations. And I had here some example, in a typical network coding system, for example, if I use the random seed to be 4 bytes, the timestamp 4 bytes, and we have this control parameter that controls how big the checksum is B, you can come up with it to be 64 bytes. So it's not that big. I also wanted to show you that we can also analyze what is the probability that a polluted packet will pass. Why would a polluted packet can pass such a verification scheme? Can anybody think about? Collisions or just random guess, right? The attacker is just lucky. So basically that's what happens. So if he's very lucky, what we can actually show that there is obviously some probability that a packet can pass, and that probability it's actually very small. We can also show that what is the probability if you're doing the batch verification based on how big is the window for the batch, and also what we can also show is that if you want to repeat the procedure, what will happen. And I have here an example, basically that if I look at the typical network coding system and with the B parameter of just 2 that I was mentioning, basically 1 in 65 5036 polluted packets can pass over the first hop. So that's actually a very small probability. And even if it passed, then with this 1/4 billion, he's going to be caught at the second hop. So that's even better. But, and this is where it gets interesting, obviously you never get so, I just focus and I keep showing you, right, what is the cost of cryptography and how we're not going to pay that cost. But nothing comes for free. So there is something that you do pay with this scheme that I described. Anybody paid attention and think?
Like latency will go up?
Yes,
Yeah.
very good. So that's actually what happens. Now, again, I didn't give you all the details. There are things that you can improve using a technique that is called pipelining. But the reality is you cannot, or with the scheme that I just described, a node will not forward the packet immediately. Okay? That's not what we want. Because I told you before, what we would like, if there is no attack, we would really like not to feel at all the cost of the scheme. So DART delays, as you guys observed, it delays the packets for verification. And what we actually would like is to delay only the polluted packets, right? The correct packets, we want to send them immediately. Obviously, we don't know which ones are polluted and which ones are not before we verify them, okay? So we have to make a decision of how are we going to start this. So what we came up with is some type of adaptive scheme. And we're going to start under the assumption that there are no attackers, which means we're going to be positive, optimistic. So what we want to do is to forward packets without delay, but we cannot allow we will need to verify the packets eventually. So the fact that a packet is forwarding that without delay doesn't mean that that packet will not be verified. It's just like I will not verify it at that moment. So I'm taking a risk. The risk that I'm taking is that that packet maybe was polluted. If the packet was not polluted, I'm good. I got the performance and all that. If the packet is polluted, I'm taking a risk. So that's why I don't want to always forward packets without verifying them. So I want to constrain how many hops a packet can be forwarded immediately without delay. And the way I will do that is by using some additional information on a packet, which is going to be a hop count. So again, ideally what I want to restrict for how long a polluted packet can travel. And I want, if there was no attacker, things are always going to work smoothly. So I'm going to show you the details of the scheme. So I'm going to add on the packets a hop count, which basically will say how many hops as the packet traveled since the last verification. When the packet is verified, that hop count will become 0. And for our purposes, actually, we don't protect this hop count. And we can brainstorm about why we don't protect it, what can go wrong. So ideally, what an attacker wants to do, obviously, if the attacker puts the hop count to be very small, not to his interest, right? So the only thing that he can do is he wants to make it very large. And because if he makes it very large, then we're not going to verify too long. Now, at the same time, in order for the attacker to really be able to travel for a certain number of hops, because it's going to be verified all the time, it really has to have kind of a chain, which is a little bit more difficult to achieve. So in our case, we made the decision that it's not worth it to protect it. So this is how it will work, exactly as in the things before. Now, nodes are going to be in two modes. They either forward immediately or they delay for verification. So we're going to have a forwarder time, and we're going to have this additional H hop count that will be on a packet. And this is what a forwarder node will do, waits for the packets, and he will have to decide when he needs to verify the packet immediately.